Okay, so next we have Matea Gosenca, and from University of Vienna, and she will talk about ultralight dark matter. So,
okay, thanks for introduction. Yes, I'm Matea Gosenca. I'm a postdoc in Vienna, and I'm going to be talking about multi-field ultralight dark matter. So first of all, we've seen this slide a few times today, so I'm not going to spend much time on it. I would just like to say that all the observational evidence agrees on something, and that is that 85% of the matter in the universe is dark. And we have a beautiful description for this, which is called the cold dark matter. And this assumes that this dark matter is cold, dark, and collisionless. Of course, all of these assumptions can be challenged, and they are challenged by these other models. So coldness is challenged by warm and fuzzy dark matter. There could be milli-charged dark matter, and collisionless stuff can also have, there could be self-interactions in dark matter. So I'm going to say here that while we have this good description, which is the cold dark matter, this is not really an explanation. So for an explanation, we would expect some kind of new massive particle or object, or potentially modified gravity. So if there is a new particle or object, there is like a wide sort of parameter range for the mass of this particle or object. Here on the high end, we have the primordial black holes, then we have WIMPs, we've heard a lot about this today. And then sort of in this very light range, there is an interesting property that for these light particles, the Broglie wavelength is actually larger than separation between the particles. So that's why we get this wave-like effect. And there's the QCD axion, and what I'm going to be talking about is this sort of 10 to the minus 22 to 10 to the minus 18 electron volt ultralight or fuzzy dark matter. So the model that describes ultralight dark matter is just described by a scalar field, which obeys this Lagrangian. And in the non-relativistic limit, we can derive the Schrödinger-Poisson system with this. There's also the possibility to add another potential, so the self-interaction term here. And this is something I'm not going to touch in this talk, but there is this option of extending this model. So the Schrödinger-Poisson system, there is an interesting sort of property of this field, which is the Broglie wavelength, which goes as 1 over m times velocity. And the phenomenological property of the system is that on large scales, so scales that are large compared to the Broglie wavelength of the field, it behaves just like cold dark matter. So these simulations actually show here for the fuzzy dark matter and here for the cold dark matter in comparison, there is very little distinction. But then when we go to the smaller scales, which are sort of more comparable to the Broglie wavelength, we see that there are this deviations from the cold dark matter model. So first of all, there's the solitonic core in the center, and this core is surrounded by these wave-like effects. So we call these interference patterns or granules. And this is something I'm going to be talking a lot about in this talk. So to model this rich phenomenology of the system, we have to do numerical simulations. And the code that we developed is called Axionics, is based on these two libraries, AMRX and another code NIX. We solved the Schrödinger-Poisson system on the grid, possibly with a cosmological background. And very importantly, we use the adaptive mesh refinement so that we can really increase the resolution in regions of interest. It's very highly parallelizable, and it's also publicly available, although this is already by now a bit of an old version. If you want to use it, don't use this, get in touch. So, okay, while Axionics was designed to really solve the cosmological evolution, for this project, I wanted to have something a bit more cheap. So I wanted to really be able to simulate isolated halos. And this can be done by using this eigenfunction method. So here the wave function is actually decomposed into these eigenfunctions, which have a radial and a spherical part and some random phase. And with this, we can really like sort of ad hoc design any sort of halo that has this solitonic profile in the center and then NMW, for example, in the outskirts. And here it is. So here's an example of such an isolated halo. So this is actually the entire box of the simulation. And because this really goes, this density goes to very low values at the edge, we can use the periodic boundaries. And we will be interested in this behavior of these granules in the center around the soliton. So, so far, all I've told you was really just one field, ultralight dark matter. So, but actually, if you look at these papers that first motivated this from the string theory for these really light fields, they all claim that you don't produce just one field, you produce several. For example, this paper by Marsh, there is the most likely value here for the number of fields is around 30. And there's also some other papers that talk about how the masses of the fields are distributed. So really the reason that people consider one field is because it's kind of like the simplest first thing to do. But actually, if you have one of these ultra dark matter fields, you will probably have more. So the way we model this is really just now, instead of one Schrödinger equation, we have as many as we have the fields. So this is now the field which is generalized like this, and they're all coupled just by through this gravitational potential, which still obeys the Poisson equation, where now the density comes from the sum of the contributions of all these fields. And here are the results. So this is like these are like 3 different simulations. First one with just one field, then with 2 different fields, and with 4 fields. And so the first thing to notice here is really that this central soliton is not that much affected. If anything, it's even a bit more pronounced here in the 4 fields. That the reason for this is that the soliton is always in the center and it kind of overlaps. But if you look at the granule structure, you can see that as you increase the number of fields, it becomes a bit more smooth. And the reason for this is that, you know, the granules don't necessarily overlap in all different fields, but they can be at different positions in different fields. So it's really like an averaging process that makes this a bit more smooth. So then we can also ask how much smoother this is. We do this by defining an overdensity in the usual way, and then looking at the 2-point correlation function. So this is just taking 2 different points in the halo and calculating the overdensity and then averaging over many of these pairs. And what we can see is that as we increase the number of fields, this 2-point correlation function becomes lower. So this really means that it is really smoother. It doesn't just look smoother, but it is. And it goes, so this correlation factor goes as 1 over n, which directly translates into the overdensity going as 1 over square root of n. And this is, in fact, in agreement with something called the vector dark matter, where in this paper, they actually considered, so they did simulations of the vector dark matter, which corresponds to what we would have as 3 fields in our case. So this goes as 1 over 3. So this is a good agreement. And we could also, so far we had actually all the fields had the same masses, but the granules were not correlated. So there was like a random phase to each one of them. But we could also simulate this for different masses. So here we had a scenario where like one of the fields was twice as heavy as the other one. And then when we look at this correlation function, we also see the same kind of behavior, even if the masses are different. Now you could ask, okay, so these halos are really smoother, but will they stay that way? Like, because you could imagine that if you had an overdensity in one field, which will be imprinted on the gravitational potential, that will also sort of start an overdensity in other fields. So for this, we calculated the 1-point covariance, which is now not taking 2 different points in the halo, but taking actually the same spatial position in 2 different halos, right? So this delta 1 is one field, the delta 2 is the other field. So this 1-point covariance is going to be 1 if the fields are maximally correlated. It's going to be 0 if there's no correlation, and negative or -1 if the fields are perfectly anti-correlated. And what we find is, so these points are now for like different snapshots. So every single snapshot we calculate is 1-point covariance. And what we find is that for 2 or 4 fields, a little bit of this correlation develops, but it actually stays well at sort of around 0.1. So this is not meaningful enough that you would say that the smoothness goes away. We also compared this to like isolated single field simulations to see how much of this is really just noise. And although there is a little bit of noise, we actually think that this small amount of correlation is there, but it's not enough. It's also not growing with time significantly. Okay, so why do we care about this? As you're probably well aware by now, ultralight dark matter has a lot of constraints. And here I'm listing sort of either the most severe ones, which are the Lyman alpha and this stellar heating, or the newer ones, pulsar timing arrays, which we heard about on Monday, and the lens radio jet. But what we really wanted to look at is these stellar heating of stars in faint dwarfs. So the idea in this paper was that if you look at the stars traveling around in an ultralight dark matter halo, as they pass these granules, they will get velocity kicks from interacting with the granules. So because this is imprinted on the gravitational potential, every time the star passes a granules gets a little velocity kick, which depends on the mass of the granule. And then the total velocity dispersion is now proportional to the number of sort of encounters with the granules and this velocity kick squared. And so in this paper, they found that the velocity dispersion increases with time, and also this half-light radius increases like this. These are, so the gray regions here are for Segway ultra-faint dwarf, and they're basically saying that this is ruling out fuzzy dark matter because of these interactions with granules would heat up the stars too much. So then if you actually plug these things in, you see that this observed velocity dispersion has to be, because it has to be greater than the one produced by the granules. This goes as 1 over m cubed, when m is the mass of the field. And we checked how this works for the multifield case. So here the number of encounters with granules is now is increased by the factor of n, because the stars are encountering many more granules. On the other hand, the mass goes down by n, and because this is squared here, you get 1 over n contribution from more fields. On the other hand, so this is for the case where all of the fields have the same mass, but we can also consider the scenario where, for example, one of the fields is much lighter than the others. And in this case, because this light field really dominates the heating, you even get like an n square factor here. Okay, so I just want to quickly mention one kind of extreme limit of this multifield thing. So you could, for example, consider having just 2 fields where one of them behaves like fuzzy and one of them is really, the mass is so large that it behaves like cold dark matter. Or you could have another component which actually is cold dark matter. And so in this paper, we studied how much fuzzy dark matter you need in terms of fraction to get some of the wave effects present. And we found that sort of between 10 or maybe 30% fuzzy dark matter or ultra dark matter, you will get a core and you will have wave-like effects. Okay, so this brings me to my conclusions. I'm going to say that ultra dark matter represents a compelling dark matter explanation. There are a lot of constraints which are sort of closing the gap for the allowed mass of the particle that describes this. So with the multi-field scenario, we can alleviate some of these observational constraints, and in particular the ones that are based on the granular structure of the inner parts of the halo. Okay, thank you very much.